In today's clip, we'll look at a classic conceptual question. The question goes as follows. A car is driving at constant speed of 20 meters per second on a road. The car brakes suddenly, locking the wheel, causing the car to skid to a stop. At what point would the kinetic friction due to braking be the largest? And we're giving you three option of points. The first point is at A, where we have just a flat road. Then there's point B, that is at the bottom of a hill. And then at point C, which is at the top of the hill. The fourth option is to say that the kinetic friction will be the same in all three locations. So I strongly advise you to hit pause, try to think about it on your own. Even though it's a conceptual question, remember that free body diagram are still your friends. Alright, hope you have your answer. So now the next question is, how do we link all of this together and what's basically different between A, B, and C? The first thing to realize is that we are in a situation where we are asking for the friction force. And the friction force we know will just be mu k times the normal when we're dealing with kinetic friction. We know it's kinetic friction because it says that it's locking the wheel. If the wheels are locked, then there is sliding, and sliding refers to kinetic friction. So then we can go back and see what are the forces that are actually involved in our question. And when the car will be at point A and will start to brake, we know that there will be the force due to gravity that will be important, there will be the normal force that will be important as well, and finally there will be the friction force that will go against the motion. And these are the three forces we're dealing with. So in order to compare the friction force, since we know it's the same road and we can assume the tires are the same all along, so mu k does not change. So which one has the possibility of changing between one and the case and the next is really the normal. So that's what we need to focus on. So we'll focus on what's going on the vertical axis. So not surprisingly, I believe, I will get started by just drawing the free body diagram at all 3 points. But as we discussed, the forces that are involved in this situation are actually the same in all 3 positions. So I will just recopy exactly the same thing 3 times in a row. And what we want to consider now is how actually things differ between these 3 cases. And where we will see the difference is in the fact that when we're at the bottom of a hill or at the top of the hill, we're no longer in a straight road. So this is actually a case where we are dealing with circular motion. So at point A, the acceleration will only be parallel to Fk. So there will only be a tangential acceleration, and the y component of the acceleration will just be 0. However, when we are getting at point B, we know that there will be a centripetal acceleration that will point towards the center of the circle. And at point C, it's the opposite, because the center of the circle is at the bottom. The centripetal acceleration will now be pointing down. So what we end up getting is that at point A, the acceleration on the y-axis is 0, while the acceleration on the y-axis at B we know will be pointing upward, and the acceleration on the y-axis at C will be pointing downward. The other piece of information we need is to discuss what's going on in terms of Newton's second law. So we know that we have that F net is equal to ma. Please note that this is a vector equation because in here we really have 2 components. We'll have the tangential component and also the radial acceleration. So what we really care about is what's going on with the radial portion. So on the radial axis, we'll have that F net, let's say on the y-axis, will be equal to the mass times the acceleration on the y-axis. In the first equation for A, we know that this only tells us that the F net on the y-axis will be equal to 0. So this means that the normal is equal to Fg. In the second case, however, the F net that we will obtain, we know will be pointing up. So if it is pointing up, it means that the normal force has to be greater in magnitude than the force due to gravity. So we'll have that the normal is greater than Fg. And finally, in the third case, we have that the net force on the y-axis this time is pointing down, which means that Fg is the one winning. So we'll have that the normal is smaller than Fg. It kind of makes sense, okay? When you're going in a roller coaster, when you're at the top of the hill, you feel lighter. So that's the normal being smaller than Fg. So the last step that we need to do in order to answer the question is to realize that if we want to have Fk to be large, it means that we need to have n to be large as well. the largest value of n being what we obtain at point B, we can figure out that the answer will be point B at the bottom of the hill. Now let's look at a similar problem, but this time with numerical values. So a car is driving at a constant speed of 20 meters per second on a road. The car brakes suddenly, locking the wheel, causing the car to skid to a stop either at point A, B, or C. If the coefficient of static and kinetic friction between the tires on the road are of 0.80 and 0.60 respectively, and the radius of curvature of the hills is of 200 meters, calculate the tangential acceleration of the car for each of the 3 points. So we can extract the meaningful information from this. First, the fact that it's going at a constant speed of 20 meters per second will come in handy. Also, we have to decide between static or kinetic friction. Because we know that the wheels are locked, this car will actually be sliding, so we have to deal with kinetic friction, which is a good news because that's a little bit easier. And finally, we know that the radius curvature of the hill is of 200 meters. In opposition to the previous question, the quantity we're looking for this time will be the tangential acceleration. So before we dig in, we should try to make sense of all of this. So the tangential acceleration will be the acceleration that the car will experience on the horizontal axis at each point. This will be a constant for a small distance for point A, but for point B and point C, we're really looking at the tangential acceleration at the point, because right away, right after it's passed, the tangential acceleration will actually change. So we have three situations. The last two are clearly dealing with centripetal acceleration. So we know that centripetal acceleration will be involved somewhere in there. So the way to go is to start with the tangential acceleration. But the tangential acceleration we know comes from the sum of forces that are happening horizontally. And the horizontal forces that we have in this problem will be the kinetic friction. But the kinetic friction we know depends on the normal force. And the normal force, as we discussed a few minutes ago, depends on the sum of forces on the y-axis, which will be equal to the mass times the acceleration on the y. But the acceleration on the y will be about the radial acceleration, and the radial acceleration we know depends on v and r. So this is really the connections that we're trying to make between all of these quantities. Before we do this, though, I would just like to revisit the free body diagrams that we had before. So what we figured out is that at point B, actually the normal force was a little bit bigger than the force due to gravity. And at point C, we saw that the normal force was smaller than the force due to gravity. So this is a more to-scale example of what we're expecting to see. The other thing that I would like you to pay attention to is how we name the axes. So in the case of point A, we have the standard way of doing things, which is just call this one y and this one x, that's fine. But for point B and point C, we're dealing with circular dynamics. So the best way probably to name the axis is to use the r-axis as the one that is pointing towards the center. So in here for point B, it's pointing up. And the other axis in here is the direction of the velocity. So we call this the t-axis, the tangential axis. And same thing for point C, the tangential axis will be horizontal, but this time the center of the circle is towards the bottom, so our r-axis will actually be pointing down. This will become useful in the next slide when we start to do the direction of motion. So just restarting from the same free body diagrams, we're now ready to write our equation for the sum of forces. So for point A, we'll have that the sum of forces on the x-axis, the horizontal axis, is the mass times the acceleration. The acceleration in x plays the role of the tangential acceleration. And we know that the only force we have on the x is Fk. However, it's pointing against the axes, so we'll put the negative there, and we have minus Fk is equal to max. We can do the same trick for point B and point C. We'll have instead in here the sum of the force on the tangential axis is equal to the mass times the tangential acceleration. And the force, the only force acting is the friction force, but again it's pointing in the negative direction, so the negative sign times the mass times the tangential acceleration. And same idea for point C, we'll get actually exactly the same thing. So sum of force tangentially is equal to the mass times tangential acceleration minus Fk is equal to the mass times the tangential acceleration. So you see that for the horizontal axis, it's the same thing for all three cases. And when we look at the sum of force on the y-axis, or the radial axis, it will also be very similar. The big difference is what is the value of the acceleration on the vertical axis. So for point A, we have n minus fg is equal to 0, because the acceleration on the y is 0. When we look at point B, you see that the r is pointing up. So this means that we'll have that the sum of forces on the r-axis this time is equal to the mass times the centripetal acceleration. And n is the positive 1 minus fg. And we know that this will be equal to mar. While for the third case, the big difference is that r is now pointing down. So this means that when I do my sum of forces on the r-axis, which is equal to mass times centripetal acceleration, we know that fg is the positive one. So we'll have my fg minus n is equal to mar. From there, we have essentially everything we need. Remember that the quantity that we're looking for is really this ax or this at. So in order to find it, we need to find fk. And in order to find fk, we need to find n. And in order to find n, we will need to have the centripetal acceleration. Centripetal acceleration, it's just an easy calculation. So we know that we have ar will be equal to v squared over the radius. All right. So in here, we know that we have v, which is 20 meters per second, all of that squared, divided by the radius, which was 200 meters. So the math is easy to do in here. 20 squared, 400, divided by 20 gives you 2 meters per second squared. So we have our acceleration, and from this we can now figure out what will be the normal force in each cases. So in the first one, we'll just have n is equal to mg, and the second one will have n is equal to mar plus mg, and in the third one we get n is equal to fg, so mg minus mar. With n, we can now calculate the value of fk, which is just equal to mu k times the normal. But at the same time, we can right away calculate what will be the ax, because we know that ax will be equal to fk divided by the mass. So really what we're looking for will be the value of mu k times mg divided by the mass. So we will simply get mu k times g. Now here, please note that I forgot something important, which is the negative sign in here, which means that in the end we get a negative acceleration as we expect. In first one, the value of the acceleration will just be equal to minus 5.9 meters per second squared. In the second one, it's the same idea. We have the normal force that is written this way. So once again, we'll have that the tangential acceleration is equal to minus mu k times the normal, which is just fk, and then we divide by the mass. So in here, this will be minus. The mass in here will cancel out with this one. So we just have mu k times ar plus g, or g plus ar if you want to. So the only difference with the calculations that we did before is that we'll have minus 0.60 times 2 meters per second squared plus the 9.80 meters per second squared. So when we do the math for this one, we get the value of minus 7.1 meters per second squared. And finally, we are ready to calculate the tangential acceleration for the last case. And for the last one, it will be pretty much the same thing we just calculated. The only difference will be that we'll have minus mu k times g minus ar for that one. So note the negative sign. So in the end, when we plug in the values, we'll have minus 0.60 times 9.80 meters per second squared minus 2 meters per second squared. And once you do the math, you get minus 4.7 meters per second squared. So just as we expect, the value of the tangential acceleration will be greater when the normal is bigger and will be smaller when the normal is the smallest. And the flat road is in between the two. Thanks, hope you enjoyed.